In this video, we're going to study the domain of functions and the range of functions. So first of all, just a definition. The domain is the set of all input values for a particular function, and the range is a set of all output values. Now let's think back to our grocery store scanner example, where we're thinking of the scanner at a grocery store as a function. And it's a function because any particular type of item will only give one price. Okay, so the price is the output, the item is the input. Now clearly you are not going to expect all types of numbers to be spit out as outputs because of the fact that they're prices. Okay, so for example, you would never expect a negative number to come out if you are scanning an item and it's telling you what the price is. Okay, so what that means is that the range of the grocery store scanner is limited to only positive values. All right, so we're going to look at how domain and range can be restricted in various ways. And the first way we'll look at it is graphically. So if I look at this graph here, let's focus on domain. Okay, and so just remember, domain is the set of all x values. All right, so what I'm going to do is I'm not going to really care what the y values are on this graph. I'm just going to focus in on the x's. So I'm going to ask myself, for what x values does this graph exist? Well, over here I can see that for an x value of -5, the graph does not exist there. Okay, and it's not until I hit -2 that the graph begins, I begin to see a part of the graph. Now we do have this thing that's an open circle right here, so I'm going to go ahead and just put that there. But then from this open circle onward, for every one of the x values past that open circle, I will be able to find a point on the graph that corresponds to it. And that's true all the way until I get to 3, and I see this solid circle kind of ending things. So on the x-axis here, I can see that all the x values in this interval here, the graph exists for. So that interval of numbers is my domain. Now this open circle means that I don't actually exist at -2. I kind of like to think of the open circle and the closed circle kind of like a manhole in the street, where the open circle, the manhole cover's not there, and the closed circle it is. And so, you know, you can stand on a closed manhole cover, no problem. If it's wide open though, you're not going to want to stand on that spot. Okay, so I kind of use that to remember what's going on. So for the domain here, there's a couple ways we can express this. On the one hand, we could just say, since these are x values, I could say, well, it's all the x values between -2 and 3. And sorry, I made a little accidental mark there. I don't want to mistake that as an equal sign. And so, of course, because I have that open circle, I did not include -2, but I did include 3 since there was a closed circle there. And to make it a little more formal, I can show you something here called set builder notation. And this is just to kind of make it fancy. And so what this does is it says it's all x. This little line here means such that x is between -2 and 3, including 3, but not including -2. Okay, so this is set builder notation. What we'll use probably more often in this class, though, is what we call interval notation. Oops. A little mistake with the pen there. Now with interval notation, we're just going to try to write out an interval that describes the domain. So anytime I see an open circle, I'm going to put a parenthesis. So I'm going to say parenthesis -2, and then I'm going to put a comma and then I'm going to put the other endpoint of my interval, which is of course 3. But 3 is different than my -2 in that I can actually be at 3. And so to indicate that, when I see a closed circle, I put a bracket. Okay, so this is what we call interval notation. And I'm going to circle this one because this is going to be probably the primary way that we go about stating our domains throughout your homework and everything. So this is good to know, but I really want you to become masters of this notation if you're not too familiar with it already. All right, so now let's look at the range. So the range, I'll switch colors here, is the set of all outputs, right? Or the set of y values. Put that right there. So what I'm doing is I'm going through the y values and I'm saying, okay, where does the graph exist? So if I start down here, it's pretty clear that it starts existing at -5. Now there's no closed or open circle here, but if you just see the graph looking like it's at y equals -5, then you kind of think of that as a closed circle. So I'm going to put a closed circle right there. And as I go along up the y-axis here, there's actually multiple places where the graph exists. And that's fine. It doesn't matter if there's multiple x values for a particular y value. So all we're doing is saying, does the graph exist at these y values? And of course it does. Now one might pause right here and look and see, oh boy, over here the graph is ceasing to exist. We got this open circle. But if I go to the other side, I have a point on my graph, and so at this point we are still including these y values in the range, so I actually just keep going. And I go up until the graph actually stops existing at 4. So I'll put a little solid circle there. And so what I can see is I have a solid circle to a solid circle between -5 and 4. And so my interval notation would be bracket -5, 4, bracket. Okay. And if I wanted to use my set builder notation, I could. Y such that my y values are between -5 and 4. All right. Now, if that set notation that I was just describing isn't all that familiar to you, this next page of the notes has just a lot of examples of typical sets that you might use. A couple of things I'll point out. This one here, -∞, 3, that means all numbers less than 3. So that would be a number line that, looks like this. And it just goes on forever in the negative direction. We always use parentheses with either -∞, or as you can see down here, with +∞. And that's simply because infinity is not an actual number, right? It's a concept. So it's not a number that you could actually stand on. So you're always going to use parentheses with -∞ or infinity. And then lastly, there's this symbol here. This means it's the union of these two intervals. So if you ever feel the need to put two intervals together, to kind of glue them together, you put that U in between them. All right, so now let's take a look at a couple of the functions that you were actually introduced to previously in the notes, and let's talk about the domain and range of these functions. So the one on the left is our square root function. All right, so let's talk about its domain. So here I am. It looks like there's nothing to the left of x equals 0. But it seems like right at x equals 0, the graph starts to exist. And if we look at the actual equation, we know there is such thing as the square root of 0, because the square root is the number that if you square it, you get what's on the inside. So, the square root of 0 is going to be 0, because 0 squared is 0. So that's not a problem. And so it makes sense. We're going to start at 0. and we're going to include 0 in our interval. But then we've got this arrow here, right? So it just goes on forever and ever. No matter how far I go in the x, I'll always be able to find a spot on this graph. So I'll go up to infinity and, of course, use my parenthesis for the infinity. All right, so there's my domain. Okay, and then my range. Well, it certainly looks like the first y value that I'm going to be interested in is also 0. So I'm going to start at y equals 0 and then go on, and even though this graph grows really slowly, it does always grow. Okay, so in other words, if I want to get to a particular y value, I'll always be able to find an x value that does that for me. And so even if it takes a really, really long time, any y value I pick here, I will eventually find a point on the graph that corresponds to it. So that also goes up to infinity. Okay. All right, now here's another graph, our reciprocal graph, or 1 over x. And so in this one, what looks like is happening, let's start with the domain. Is because I have this arrow going off to the left here, it certainly seems like it's going to just kind of continue on forever and ever. So I'm not anticipating any starting point to this graph because of this arrow. So I'm going to say that, hey, it starts way off the page there, infinitely far back, and so I'll say it starts at negative infinity. And as I go along here, as I pick x values along here, as I get closer and closer to 0, it might become harder and harder to imagine, but it does seem like I'll always eventually hit a part of the graph as I pick x values. And yet here at x equals 0, that's another matter. So right at x equals 0, we will actually never hit the graph, neither down here nor up there. And if we look back at the equation, I think it's pretty clear why. We know that we can never divide by 0. Okay, that would be something that would be bad for this equation. And so what's happening here is that the domain is going to stop at 0. So I use parentheses, right? I use a parenthesis to say that I can't be at 0, but guess what? I can be as close to it as I want to be. So I can get infinitesimally, right, really, really close to that x equals 0. I'll be able to find a spot on the graph, even if it's way down there, if that arrow just kind of continued for me. But I can't be at 0. But then, of course, after 0, I'm free to pick things back up again, right? So if I pick a value really, really close here, eventually it's going to hit my graph. And so I can have anything to the right of 0. So I'm going to use that union symbol that we talked about on the previous slide. And then I can be anything from just after 0 up to infinity. And so my domain looks like this. Okay, and if I wanted to use the set builder notation, I could say x such that x doesn't equal 0. And that'd be a pretty simple way to say it. And then my range, I'm not going to spend too much time on that because it doesn't take too much time to look at it and realize it's the exact same thing. I can go from a y value of negative infinity up to, but it looks like I can't quite hit 0. So I'll say negative infinity to 0, and then 0 to infinity. So the domain and range of both of these functions are actually identical to one another. And I showed you both the interval notation and the set builder notation. Again, I only need one of these. I don't need you to give me both, but I just wanted to kind of show both ways of answering this question. Now, with these two graphs in mind, let's understand that the reason that their domains were restricted, the reason there were x values that I couldn't put into the function, is because of the nature of these equations themselves, right? So we know that we can't do something like take the square root of -4, right? The square root of -4, that would have to be a number that if you times it by itself would give you -4. But no number, if you times it by itself, can ever give you a negative. Okay, so that's why the negatives didn't work there, and so we just don't allow them to be a part of our function domain. And here we know that, hey, dividing by 0 is a bad idea, so we didn't do that, and we restricted our domain to kick 0 out. So with that in mind, we can kind of put these down as principles, right? So when we're trying to determine our domain, we always remember that we're not allowed to divide by 0, and we should never take the even root of a negative number. Okay, I say even root because, this is the square root, but we know there's such things as cube roots, fourth roots, fifth roots, etc. And so what this principle is saying is even roots get you in trouble, square root gets you in trouble, fourth root gets you in trouble. And so you have to watch out to make sure you're not plugging in inappropriate x values into your function. And then lastly, sometimes applications can make your domain restricted. So here's a real simple example. Suppose that we have, we're considering a function, so a of r is equal to pi r squared. That should look familiar. A of r is the function that gives the area of a circle as a function of the radius. Okay, so what would the domain of such a function be? Well, I'm not dividing by 0 ever, and I'm not taking the square root of anything, so number 1 and number 2 don't apply. But of course, just the application itself, we understand it makes no sense to talk about a negative radius, right? That doesn't make any sense at all. And one could even argue that it doesn't even make sense to talk about a 0 radius, okay? So, I could take an argument where we would include 0 or not 0. We'll include it so that it's like I don't know what that would mean, the circle of area 0. But definitely we want to kick out the negative. So this would be our domain just based upon what the function is supposed to represent. So in this example, what we want to do is take functions that are expressed as equations and be able to tell from them what their domain ought to be. All right, so we know the rules we just talked about were that we can never take an even root of a negative number, and we can't divide by 0. So of course in part A there's no roots anywhere, so the danger is in dividing by 0. So what we need to know is, okay, when is it that x squared minus 16 is going to give me 0? Okay, well, there's a number of ways we can solve this, and we've explored those, but I'm just going to go ahead and use the method of getting the x squared by itself, since I've got no middle term to that quadratic. And when I have x squared equals a number, I know that I can solve it by saying x is plus or minus the square root of that number, which is plus or minus 4. And so remember, of course, the reason for this is that, of course, 4 times 4 is 16, but so is -4 times -4. So there's two different solutions we could get. And so from that information, what we can see is that, we just solve for what we don't want, right? So we don't want x to be -4, and we don't want x to be 4. Right? Those would be bad. And in fact, when I have it written like this, that actually basically has our set builder notation done for us already. So actually, I could just, if I wanted to write it in set builder notation, there's my answer. But also, a lot of our homework questions will specifically ask us to use interval notation. So if I did that, I want to start out by thinking that, normally a function could have any value, right? It can certainly have any values that are less than these two problem spots. So I'm going to start my domain off at negative infinity, and I'm going to go along until I hit one of these problem spots, and of course negative 4 is the first of those problem spots. So I say I can be anything from negative infinity to negative 4, and then I'm going to pick things up again right after negative 4 until I hit my next problem spot, which would be 4. And then I'll pick things up again after 4, and there's no more problem spots, so then I can ride off in the sunset to infinity. And so there's my domain if I'm writing it in interval notation. All right, part B here. Okay, we're not dividing by anything, but we can see we have an even root. So we know that we can't take the square root of a negative, or to frame it the opposite way, we can take the square root of positive numbers or 0. So what we want to make sure is we want to make sure that 2x minus 6 is always greater than or equal to 0. But that just gives me a little inequality that I'm able to solve easily. So we end up with x is greater than or equal to 3. And just like the last time, solving this inequality here really has it all set up for set builder notation. So there's your answer in set builder notation, or in interval notation 3, and we're including 3, right? Because we have greater than or equal to up to infinity. Now in part C, we really have both situations happening. We've got a square root, and we have the potential to divide by 0. So what we really have to do here is just, attack these one at a time. So on the one hand, I know that a minus 3, I got to watch out for when that's 0. And of course that's going to happen when a is equal to 3. And so, well, when I say a equals 3, I'm really stating what I don't want to happen. So maybe what I should say here is a should not be 3. Okay, so we'll kind of keep that in mind here. On the other hand, we've got to watch out to make sure we're not taking the square root of a negative. So we want to make sure that a plus 4 is always bigger than or equal to 0. All right, but that's easily solved. So a is greater than or equal to negative 4. So that's the other part. Now we've got two pieces here, so it's not a terrible idea when you've got two pieces to your domain. Just make a little number line. So here's 0, here's negative 4, here's 3. And so we can see a greater than or equal to negative 4 means I can be equal to negative 4, and I can be larger than it, but then I have to stop here where a does not equal 3 and put an open circle, since I don't want to be 3 so that I don't divide by 0. And then of course I pick things back up again. And so once you draw a little number line, then that really allows the interval notation to fall right out. So what I can do is I can say my domain is negative 4 up to 3, where the interruption is, but then right after that interruption I just pick things up again and go up to infinity. And there's my answer. All right, in part D here, we have a square root again, but then that square root is in the denominator. Okay, so when we see the square root, we automatically say, all right, well, that needs to be bigger than or equal to 0. Okay, but I actually don't want it to be 0, right? Even though that doesn't give me a problem with my square root, because the square root's in the denominator, that would cause me to divide by 0. So what we're going to do is just say 2 minus t is just purely greater than 0 in this case. Now there's two ways you can solve this. I want to remind you of both. On the one hand, you might subtract 2 from both sides. And then you look here, you got a negative in front of your t, and if you divide both sides by negative 1 or multiply both sides by negative 1, that would do the trick. I'll go ahead and divide by negative 1. But remember, when you do that, anytime you multiply or divide both sides of an inequality by a negative, you've got to flip that inequality around. So this becomes t is less than 2. Okay? And just a very quick explanation here to remind you of why that is. If you, let's again draw a little number line. So let's say I have 0 here, then I have the number 2 here and the number 6 here. Okay, let's say I wanted to divide both of these numbers, 2 and 6, by negative 2. If you divide 2 by negative 2, that becomes negative 1, doesn't it? And if you divide 6 by negative 2, that becomes negative 3, right? So that's me dividing by negative 2. So notice what happened. The relative position to one another changed when I divided by a negative, right? 2 was on the left of 6, but when I divided by negative 2, the number that 2 became is to the right of the number that 6 became. So that's just a quick reminder of why it is that you got to remember to flip that inequality. Of course, the other way I could do this would be to just say, well, how about we add t to both sides? So 2 is greater than t, but of course if you just flip it around, you get the exact same answer as we had here, so t is less than 2. So that gives us a domain and interval notation of negative infinity to 2. All right, and then finally part E, we've got this function w of y, okay, and yes, I know that y is often our output, but we do need to get used to the fact that we're going to jumble letters around, and so in this case, y is my input. It wants to know what the domain is, but let's think it through. We don't have any roots, we don't have any division by variables, so neither of the two bad things that could happen are possible here. So in a case like this, we would just say that our domain, our domain is all numbers. So in other words, just negative infinity up to infinity.